Now we'll just take up another topic for today. That is again the refreshment of refreshing the concept of elementary data structure. So we will continue with the topic of trees. Now trees is a non-linear data structure. Remember that. Stacks and queues are linear data structures. Linear means there is a relationship, a sequential relationship between elements. Like in an array, you take the array, the elements in an array. What happens? There is, whatever element you have, there is a sequential relationship. One element if you take, you can say that that element occurs after or before some element. Obviously, there will not be a before element for the first element itself in sequence in linear data structures, as well as there will not be a after element for the last element. So that's, I mean, the relationship is sequential or what we say linear in terms of the elements. So there is before and after relationship. That is why those are stacks and queues are known as linear data structures. But trees are non-linear data structures. There is no sequence as such. There is no before and after relationship. But here there is a hierarchical relationship. That is why it's called as non-linear data structures. Hierarchical relationship. The relationship here is not before and after, but relationship here is above and below. It's a hierarchy, above and below relationship. So if you see, if we take this node, let's say C, there is no before and after. We cannot say that B is before C and D is after C. There is no before and after relationship here. This is a non-linear data structure, but it has above and below relationship. That is, A is above C and G is below C. So there is an above and below relation. It's a hierarchy there, like just like a parent-child relationship. So for C, A is the parent of C and G is the child of C. So it's a hierarchical relationship and it is known as, so trees are known as non-linear data structures. Now, there is a special node here. That node doesn't have, and there's only one special one node which is special and which doesn't have its parent. That is known as the root node. So here A is the root node. It doesn't have a parent, and every tree will have a root node. If there is a node, then definitely there will be a root node which does not have any parent. Then there are several other normal terminology used in trees. That is, the nodes which does not have any children are known as leaf nodes, or external nodes. So here in this case, G is a child node, F is a child node. So G, F all are leaf node. G, F, M, I, J, L, K, all these are leaf nodes or external nodes. They don't have any children. Then the nodes which has children, like for example B, E, C, D, these are known as non-leaf nodes or internal nodes. They have children. Even node A is an internal node or non-leaf node, but it has a special property that is doesn't have a parent, so it is known as a root node. Then we need to see another thing that since it's a hierarchical data structures, there is a levels. The elements are not before and after, but the elements are placed at levels. So root node will be at level 1. Then its children, that is, in this case, A is root node. Its children B, C, and D will be at second level. Its grandchildren, that is E, F, G, H, and so will be at the third level, and subsequently, in the hierarchy, next level will be the fourth level. So level goes on starting from the root node, and then its children in the hierarchy continues. Now, There is another up from trees. Now, if you look at the previous tree, a node may have more than, may not have a children. That means it's a leaf node. If it has children, it may have one child or more than one child. So in this case, if you see node B has two children, whereas node D has three children. Node C has only one child. So if we consider, there is special kind of trees known as binary trees, where a node can have at most two children. At most two children. That means a node of a binary tree can have no children, no child, or it can have one child, or it can have two children. Not more than two children. At the most two. So in this case, if you look at this side, the larger graph, larger tree, A has two children, B has two, T also has two, H, I, E, F, and G are leaf nodes. They don't have any children, so this is a binary tree. And the level of this binary tree is A is on first level, B, C second, D, E, F third, and H and I at fourth level. Let us look at this tree, which has only left child. So here A is there, it has one child B, B has one child C, C has one child D, D has one child E, and E is a leaf node, doesn't have any children. So is this a binary tree? Can anybody answer? Is this a binary tree? Just type it in chat. Type it in the chat, man. Is it a binary tree? Anyone? If you are listening, obviously. If you are not listening, then I can't say. Anybody? Anyway, it doesn't matter. I hope you, again, people look at the recording and then try to understand. But anyway, right now you people are not awake. So let me continue the class. You people can go through this later. Anyway, this part, this is also a binary tree because every node has at most two children. 0, 1, or 2. Not more than 2. So this is also a binary tree. But this is known as, since all the nodes have left child itself, it is known as left skewed binary tree. Left skewed binary tree. But you can see that the number of levels increases here. Here, the levels of this binary tree are 5. The 5 levels in this binary tree. Whereas, if you consider this binary tree, it has only 4 levels. Now, let's move further. Let's look at another definition here, which is a full binary tree. A full binary tree means every node will have, every internal node or non-leaf node will have exactly 2 children, and all the leaf nodes are on the same level. All the leaf nodes are on the same level. Though there is also a formula also through which the full binary tree is described. Now what it says is, in terms of height, it says full binary tree of height h will have 2 power h minus 1 nodes. Exactly 2 power h minus 1 nodes. But in general sense, what we define with the full binary tree, what we say in the theoretical terminology is that a full binary tree will have all the non-leaf nodes or internal nodes will have exactly 2 children, and all the leaf nodes are on the same level. So you can see all leaf nodes 1, 2, 4, 5, 6, 3, and 7. All of them have exactly 2 children, and all the leaf nodes are on the same level. Then let us look at the representation of this binary tree. And what we need to do over here is that we need to Where is the pointer marker? I'll just take a marker here. Okay. Now we can use arrays as well as linked lists to represent binary trees. Let us first look at how to represent using arrays, that is sequential representation or sequential using sequential memory location, representing binary trees. What we will do is we will start numbering the nodes from the top to bottom and in each level from left to right. So from top to bottom means we'll start with A as we will number it as 1. In the next level, top to bottom, next level, yeah, from and within the level from left to right. So we'll number node B as 2, C as 3. The next level from left to right, so D as 4, E as 5, F as 6, G as 7. And then next level 8 for H and 9 for I. So we start numbering nodes from in level order, that is from in level from top level to bottom, and each level from left to right. And then since we are using arrays, arrays has indexes which we start from 1 to 15. Obviously, this is not language dependent. Depending upon language, the array may start from index 0. But we are considering this is an algorithm, designing an algorithm. So we are considering array starting from 1, index 1. So A is there, which is at what have we labeled? We labeled it to be 1. So it will be stored at index 1. Same way B will be stored at index 2, C at index 3 because that is how we have labeled it. D, E, F, G, H and F, G, H and I. I is at 9th index. So here we are storing at the 9th level we have given, 9th index we are storing. So this is how sequentially we represent the nodes in an array using sequential representation. Now let us look at this. Now what happens here? How is it placed? There is also array representation, sequential representation. And this was easy because all nodes were filled up at positions. But here, this is a little difficult. So what we say is A, we number it 1, label it 1. B, next level, we label it as 2 node. But in this level, B level, they could have been a node here. They could have been a node here whose label would have been 3. We consider a full binary table. Then at C, so A only 2 nodes can be there, B and any other node, but it's not there, so this is labeled as 3. So C will be labeled as 4. When C is labeled as 4, why 4? Because 2, there is nothing at 3, so 4. And then B here, it could have been a node over here, which would have been 5. There could have been a node here, which would have been 6. There could have been a node here, which could have been 7. Then comes D, which is 8, labeled as 8. So if you see, A is at index 1, B is at index 2, then 3 there is no node, so we make it blank. 4th index we have C, which is labeled as C. 5th we don't have anything. 6th we don't have anything. 7th we don't have anything. 5th, 6th and 7th, these are blank, but we have to label it. Then 8 we have D, we have at the 8th position. The same way they could have been a node here and 2 nodes of this, 2 nodes of this, 2 nodes of this. And finally, E will be at the 15th place. So the entire thing is represented as a full binary tree for labeling purpose, but when we actually, for labeling purpose, we consider this as a full binary tree. but it's not exactly a full binary tree. Only for labeling purpose we are considering, and rest of the nodes of the tree will be empty, so we don't fill them up. So now here what is happening is, if the tree is a left skewed, you can find that there's so much memory space has been wasted. That is, to store here, in this case, to store 9 elements, mean 9 memory location would have been enough index for an array. But in this case, if you look at it, if we have to store these 5 elements, we need 15 memory locations, and most of the memory locations are empty. But we need 15 memory locations. So array-based representation of a binary tree or sequential representation of a binary tree consumes lot of memory. It actually wastes a lot of memory because many of the cells, if it's a right skewed or left skewed binary tree, many of the cells will be empty. So there is a problem with respect to binary trees representation using arrays. So we move on with the next type of representation, that is linked-based representation.
Now, in the last class, we have left at the trees. Now we have to move further. Now, what we are seeing right now are the elementary data structures, or the basic data structures which is needed for the further concepts of design analysis of algorithms. Now here we have in the previous classes looked at the stacks, queues, that is their operations. Stacks, we have push and pop, queues, NQ and DQ operations. Similarly, we are looking at trees. So these are the elementary or basic data structures. In this last class, we have seen the sequential representation or array-based representation of binary trees. Now we will continue further with the linked representation of binary trees. Now in the array representation, we have sequential memory allocations, and each node is numbered from top to bottom and at each level from left to right, starting from the root. So the index represents the numbering of the nodes. But in case of linked representation, that is not the case. It is not the sequential memory that is allocated. So therefore, in this one, what we have is, we have a node which contains the element. So for example, if A is the node here, it contains the element, and then the node contains the link or the address of the left subtree and the right subtree. So each node will have an element with its address to the left subtree and address to the right subtree. So if you look at this example of this tree, A is the root node, so we have A, and then B is the left child of A. So there is a link between node A to node B. Then similarly, C is the right child, so we have the link to node C as the right child of node A. Now this process continues, and at the end, if you see, for example, the node H and node I, they both are leaf nodes, as well as node E, node F, and node G. So the leaf nodes left and right address will be null. Now there might be some cases where we may have only one child, left or right child. In that case, there will be a link from left or right child, link from the parent node to the left of the right child, and whichever child is not present, for example left or right, that address will be null. So this is the linked representation of binary trees. Now the advantage of linked representation with when compared to the sequential or array-based representation is that in array-based representation we have to allocate enough memory to store the nodes based on the numbering given to each node as the index. So there is a lot of wastage of space. But whereas in linked representation, nodes are dynamically created. So there is no need to allocate memory and then use that memory. It is actually the nodes are dynamically created depending upon their hierarchy or their structure in the actual tree. So this is what is about the tree representation. Obviously, trees also has operations of traversing, like in order, pre-order, post-order, level order traversals. We are not going to go into that detail. And whenever needed, the traversal of trees and all, whenever it is needed in the complex algorithms or throughout this course, then we will try to look at those operations. Then the other thing is even trees has like stack has push and pop operations. Even trees has the operations known as insert and delete. And we will try to look at those operations in the next topic known as dictionaries. So this was all about the trees or the binary trees.